We need to finish up with section 1.9 and hopefully we'll make it to 1 point, or sorry, not 1 point, where we get to move on to 2.1. So chapter 2. I was curious, and maybe you guys could tell me like in the chat or out loud if you prefer, like how familiar you are with like matrix multiplication. We did talk about how to multiply a matrix by a vector, and I just wasn't sure, like, have you seen this before? Do you like need me to step through it slowly, or is it more review? Like, that's what I'm kind of looking for. Not familiar. Okay, well, if someone's not familiar, then yeah, we should step through it slowly just to make sure everybody's on the same page, which we will do when we get to section 2.1. But we are not there yet. Okay, I need to start this. Oh, oops. Okay. There we go. Okay. So we are talking about section 1.9. And I forget what the name of this is. What's this called? Something about matrix transformations, is that right?
I think it's the matrix of a linear transformation.
Okay, great. The matrix of a linear transformation. I'm just gonna abbreviate LT. Oh, I didn't write this correctly. Matrix of a linear transformation. So I think what we left off with last time was this theorem. So it tells us how to find the matrix of any given linear transformation. So if we have a linear transformation, so from Rn to Rm, so if this is a linear transformation, then there exists a unique matrix A such that T of X can be written as that matrix A times X. So we saw that these were, when we had things of this form, those gave us examples of linear transformations. And in fact, every linear transformation can be written in this way. So there are no other types of linear transformations. Okay. Okay. And furthermore, it has a particular form, this unique matrix A. And that is that we just form a matrix by taking for each of the columns T applied to the unit vector E1, starting with E1, we'll then have E2 as the next column, so T of E2 and T of En. And remember that, so for EI, this is the vector with zeros except for a 1 in the ith entry. That's what that object is. Right. Okay. So we're going to go ahead and prove this. Okay. And so what we can do is consider a vector X. And we talked about this identity matrix, right, last time. That was the matrix that was all zeros except for the diagonal, right? Along the diagonal, it had ones. And so It was always square, so it had the same number of rows as columns. And when we multiply by it, it does not change the vector at all, right? So we could just write it as this identity matrix times X, and that doesn't change anything. So these two things are equal, right? And then we can expand this out. So we know that this identity matrix is made up of these vectors E1, E2 up to En. Oops, not times Xn, times the vector X, right? And then we know that matrix multiplication, we can rewrite this. So this is a matrix times a vector. We can rewrite it as a sum of vectors where we just take the entries. In fact, let me write it. I'll write X as a vector so we can see this more clearly, right? So it's a vector with these entries, and then we can just expand this out to be x1 times e1, x2 times e2, up to xn times en, right? So we just write it as sum of vectors. And then, so we've done this expanding out, then we look at t applied to x. And now we know that we can rewrite x in this way that we just did. So we're just going to plug that in. So it's e1 up to xn times en. And then we can use the fact that t is a linear transformation. So that means that we can split these into t applied to each of these vectors, and we can pull out those scalars x1 up to xn. So just doing all of that at once, we get x1 times t of e1 up to xn times t of en, like that, right? And then we're going to put this back into matrix notation. So sort of like what we did in our first step here, but we're going backwards. So we're going to rewrite it as t of e1, t of e2. So just forming a matrix with these columns of en, and we get times the vector x1, x2 up to xn. Okay, so we are here, and this is exactly what we said A would be, right? So we're just going to replace this with A. So that means we get t of x is equal to A times x, where A is the matrix formed by taking t of each of those unit vectors and then forming columns from those. Okay. Okay, so what this means is that we get a unique representation of any linear transformation. Right, that's good to know. So we do have this correspondence now. So a matrix can define a linear transformation, and a linear transformation has an associated matrix. So they're very closely related, but they're not exactly the same things, because a linear transformation is a function, right? It takes in an input and spits out an output. A matrix by itself is really just a collection of numbers, or you might put variables in it, but it's still just like an ordered pair or a vector. We're just putting things into particular places in a particular order, right? That's what it does for us. So they are different, but there's this really nice correspondence between them, right? Okay, so I would encourage you, if you haven't looked already, there are a bunch of examples in this section. So see the examples in the textbook. I think they are linear transformations from R2 to R2. And we did talk about, I think, a few of them, but there's a bunch more And these start on page 74. So it's good to look at like sort of the different types of linear transformations that you can get and what their corresponding matrices would be, right? There's one that is really useful to know. Is really a class of transformations, and these are the ones, I guess, transformations to know. These are rotations by an angle theta, right? So this is right. So the idea is that you have your vector u, and the transformation just rotates it by theta, and you get a new vector. Oh, it should be the same length. Oh, oops. T of u. So it doesn't stretch it at all, it just rotates. These have a particular form, and we can figure out what that would be. So if we want to figure out what the associated matrix is, right, find our unique matrix representation. So what is the associated matrix? We look at the images of E1 and E2, right? And once we have those, we just stick them in a matrix, and that is our associated matrix for that linear transformation, right?
So the associated matrix is like, so you take the identity matrix and where each of its columns go under a linear transformation.
So I wouldn't think of it that way. I mean, I suppose you could, but I think it's better to just separate out. So those columns forming your identity matrix will be these E1 and E2,
Right.
and E3 and so on. So just think of making a matrix by applying T to each one of those and then sticking those into.
Okay.
Yeah. Great. So we're just going to picture, so instead of like drawing two, like drawing the domain on one side and the image of those things on the other side, we're just going to keep it all in the same picture, like I did in this first part, right? Because it'll be a little easier to deal with. So the idea is we have, so I'll try to make them the same length. What's that? 1, 2, 3, 4, 5, 6. Okay, so here would be my E1, and here's my E2, right? And we're going to rotate by an angle theta. So let's say theta would be here. And this is my image of E1 under this transformation, right? Then we can figure out what this point would be, right? So we're just rotating from the x-axis, along the x-axis, to this point, which will be given by, so you should know this from trigonometry, right? What would this point be? So what would the x coordinate of this be?
Cosine?
Yeah, cosine of theta. And then the y coordinate is given by sine of theta, right? Okay, so that's our image of our first vector, right? So we could start to form our matrix by writing this as, so we know that it's going to look like T of E1 times T of E2. In fact, let's just write down the matrix. So this will be our matrix A. That first column is going to be cosine theta, sine theta, right? And then we just have to figure out what the other one will be. So the image of E2. Okay, this is also rotated by that same angle, so try to make it consistent just a little bit. Okay, so we rotate again by theta, right? And then we just want to figure out where this vector ends up, right? And that will be given by, so looking at this, maybe I'll do this thing. Just do this in a different color so it doesn't get all smushed together. So this distance right here, that pink line that I drew, that's gonna be the sine, sine of theta, right? Because this vector has length 1, we know that. We rotated it, it didn't change in length, so it'll still be length 1, right? And so that if we take sine of theta, we would get the x coordinate over 1, but that pink line, so this would really just give us the length of that pink line. It doesn't tell us that it's in the second quadrant, right? Second quadrant, right? So we actually have to make this x coordinate negative. Oh, right. This is what we get. So really, x will be negative sine of theta. And then to get the y coordinate, we just take the cosine. So that would be this length right here. It is positive, so we don't need to worry about changing the sign at all. We take cosine of theta will be y over 1, so just y. Or maybe I'll write it in another direction. So y equals cosine of theta. So putting these together, those are x and y coordinates, or x1 and x2 coordinates. And so we would get that the vector is negative sine theta and cosine theta. Right.
And me. So I think I understand like the matrix algebra part, but it's been a really long time since I've done any trig. Like I think the last time I did trig was in high school. So I don't really know what's going on with like cosine and sine.
Okay, well, in that case, I don't think we're gonna be doing much trig. So, this is gonna be like the most exposure I think we'll get. I mean, maybe there'll be applications and things like that, but I don't know. The important part is that we have this nice form for a rotation, linear, like a linear transformation that is a rotation, right? And this works for any angle theta.
Okay.
Okay.
Thank you.
Yeah, no problem. So we can check because we had last time we did an example where we had this linear transformation. It was 0, 1, minus 1, 0, right, times x. And we figured out what the images of the two unit vectors were, your E1 and E2, right? And we saw that this is a rotation, or so this is a rotation by 90 degrees, or pi over 2. Right? And we can check that our formula works for this. So we should, if we plug in theta equals pi over 2, we should get this matrix. Oops. Be careful with that. This matrix right here, right? So plugging in, we would get cosine of pi over 2, sine of pi over 2, and then negative sine of pi over 2, cosine of pi over 2 times x, right? And then if we evaluate each of these, so cosine of pi over 2 is 0, so we will get zeros there and there. And then sine of pi over 2 is 1, so we'll get 1 and minus 1. And that is exactly what we had before, right? Okay, so this does work. And it's a convenient way of, writing down a matrix. If you want a rotation, you want a linear transformation that is a rotation in R2, then this is how you would go about finding it. Okay, so it can be really useful. Okay, so now we're going to talk about two different properties of functions. So one-to-one and onto. We'll start with onto. So an onto function. So this definition is going to work for any function actually. So this is I'm going to state it for a function from Rn into Rm, but it does work for any function. It is a property that you could talk about for functions that are not linear transformations, but of course we are going to focus on linear transformations because this is linear algebra. So just to keep that in mind, our definition, we say that a function is, so we'll say a function from Rn to Rm is onto if for every b in the codomain, so on the target space side, for every vector there, we can find where there exists a point or a vector, sorry, x in the domain such that t of x equals b, or that point x, that vector x gets mapped to the vector b, right? Okay, so this is the definition. Some other ways to think about this. So we can think this means that every vector b in the codomain or target space gets hit by the function or covered by the function, right? So anything in the codomain has a corresponding point in the domain that gets mapped to it, right? So it gets covered by the function. Okay. Another way of seeing this is that the range, so that remember the range is the things that actually get hit by the function. So the range is equal to the entire codomain. So the range is always a subset of the codomain, right? It could be equal to it, but it is always contained in it. And so this is saying that the range is the entire thing. So since we're talking about a function from Rn to Rm, this means the range is all of Rm. Right, so we're going to be consistent. So Rn, so n will be the dimension of our domain, and m will be the dimension of our codomain, so that we don't get things mixed up. Okay. Another way of stating this, so in the language that we've been using to talk about linear transformations, we could say that this means that t of x equals b has a solution for every b. Right? Remember, this was one of the questions that we were interested in answering before, right? We talked about this question. And you may remember that this was equivalent to saying, so if this does happen, if t of x equals b has a solution for every vector b, this means that the columns of A, that associated matrix, so you could also see this as AX times B, that equation. So this is the associated matrix of T. The columns of A span what?
Rn.
It would be Rm, but yeah. Right. So Rm, the columns. So just thinking about where the columns live, like what space are they in? T.
Oh, yeah, Rm.
Yeah, each of these vectors, these are vectors in Rn to Rn. Yeah.
I'm curious, why is that true? I don't quite get it.
Why
like,
is this true?
Because you multiply A times the vector of X to get like the V vectors that span Rm, but I don't know why that means that the columns of A span Rm.
So, okay, so we had this question, like, does this has a solution for every B, right? This was a question that we asked. And we said that this did happen. We had a solution for every B. For every B, if B was in the span of the columns of A. Does that ring a bell?
Yeah, okay, so A vector X has a solution for every B vector if the A matrix, wait, this is weird. If the columns of A span Rm.
Right.
So that's how it's all like tied together.
Yeah, it's all tied together. So it's the same thing as asking, is this augmented matrix, does this give you a consistent system, right?
So it's similar to the homework questions somewhat. In that case, it's like, I think they asked them that in the homeworks.
Right, there should have been, yeah, a question like this in the homework. Yeah, yeah, so everything is interconnected, and I know that that makes it kind of confusing, but it's also like the power of linear algebra. It's that everything is interconnected, and we have all of these different ways of thinking about it. Right. Okay. I think that's okay. And I'm going to leave a space. So there's one more thing I want to add to this list, but first I'm going to do an example, and then I'm going to come back and fill that in. Okay. So here we'll have an example of a function that may or may not be onto, right? So how do we figure that out? So say we have a function t that's given by, in fact, let me move this down. Let's see, 1, 0, 1, 0, 1, 0, 2, 1, 1. Okay, so this is its associated matrix, right? And it defines the linear transformation. So this is a map from R3 into R3 because we have a 3 by 3 matrix, right? So it's R3 to R3. Okay, so we want to know whether we get a solution. So do we get a solution to Q of X equals B for every B, right? That's our question. And we can answer this by looking at the augmented matrix, where we'll just plug in an arbitrary B, right? So we'll have, this is our matrix, and then we augment with an arbitrary vector B that has entries B1, B2, and B3, right? And then we want to row reduce, right? So first we will take, do R3 minus R1. So I'm going to like abbreviate this notation a little bit. Hopefully you guys still understand what I mean by this. So I'm replacing row 3 with row 3 minus row 1. 0, 0. We would get -1 here. And we would get B3 minus B1. Right. And then this is almost in row echelon form, right? We just, in fact, we don't need leading ones, do we? So I guess it is already in row echelon form, but let's just multiply R3 by -1 to get leading ones all the way across. So we would get B1 minus B3 here, and then B2, B1, right? Okay.
Do we want to put it into reduced row echelon, or would regular echelon be fine?
So just to like fully answer the question and actually demonstrate like a solution for every B, I'm going to fully reduce, but you would actually know. So what do you know at this point? Does anybody want to take a guess?
At this point, since there's no free variables, so we know that it's going to be consistent for every value of B. Like we aren't going to have any instances where
So
like 0
right,
equals
so
a number.
it's not that there's no free variables, it's that we don't have any rows without a pivot.
Rows without a
Like, every
pivot.
row has a
Okay,
pivot.
thank you.
Yeah, if you have a row without a pivot, you could possibly have an inconsistent system for some values of B, right? So really already we know that, so at this point, we know that this will always be
Consistent.
exactly consistent.
So then that means the
Okay.
rows,
Question.
that means the columns of this matrix span R.
Right, yeah, exactly. It does mean the columns of the matrix span R3, which is our on the codomain side, right? Okay, but just to demonstrate, so what the vector will be that will hit that arbitrary vector B, like we could write down its formula. To do that, we could just keep row reducing. So I'm just gonna skip over this and keep going. So I can take row 2 minus row 3, and that will give us 0, 1, 0. Get 0 here, and row 3 stays the same. And we would get B2 minus B3. And then I'm going to do one more step in the same thing. So row 1 minus 2 times row 3 will eliminate this 2, and we'll get B1 minus B1 plus B3. Oh, oops, times 2. So
Pardon me.
yeah.
So for the B vector, the second row, that would be B2 minus B1 plus B3?
For the second row?
Yeah, because it's R2 minus
Yeah,
R3.
I got that as well, yeah. Sorry. Minus B1 plus B3, right?
What is the first thing, the first part? Like B1 minus 2?
Minus 2B1 minus, sorry. Let me clean this up. 2B3.
Cool, thank you.
Okay, yeah, no problem. Okay, so we can simplify this a little bit. So I'm just going to 0, 0, 1. Combine those, so I get negative B1 plus 2B3. We get B2 minus B1 plus B3 and B1 minus B3. Great, so that means that our solution for that arbitrary B will be just the vector where we just plug in these values. And so this will depend on what vector B you started with, but this always gives you a unique solution, right? So since no matter what B is, we always get a solution and we just would have to plug in those values, this means that T, that transformation that we started with is onto. And we've just demonstrated that really using the definition, right?
Can we do a thing where like we put it out into like the parametric form and then it's like B1, B2, B3 are like can be any real number? Do you know the thing that I'm talking about?
Yeah, yeah, we can write it as, okay, so I'm just gonna reorder this because it will help me not make mistakes. So B1, negative B1 plus B2 plus B3 and B1 minus B3. Then you can do B1 times negative 1, negative 1, 1, B2 times 0, 1, 0, B3 times 2, 1, negative 1. Okay, so we actually already made the observation that once we got it into row echelon form, we could tell that this was consistent by the fact that every row had a pivot, right? So we had a pivot in every row. That means that we can't get an inconsistent system, which means that we'll always get a solution. So the last thing I wanted to add to this was that A has a pivot in every row. Okay. And if we look at the ways to think about this being an onto function, it's not the most intuitive way of thinking about it, right? But it is the most computationally useful. You have to do the least number of computations or work to figure out whether A is or T is onto if you use this way of thinking about it. So this is probably the most useful, but not the most intuitive, right? Okay, so these are good to keep in mind, especially these last three ways of thinking about this. Okay, so great. I think I do want to write this out. So just to be clear, what can happen if a row does not have a pivot, you can get, where's the, we could get an inconsistent system. And in fact, we will for some values. So we definitely will for some values of B, or some vectors B. So if you want to think about an example, say our matrix was given by 1, 0, 0, 0. And if we look at the augmented matrix that we would be trying to solve, if B2 was non-zero, we would get an inconsistent system, right? So that would be the issue. That would mean that not every vector B gets hit by this transformation. So this is inconsistent if B2 is non-zero. So not every, so what do I want to say? How do I want to put this? So we get a solution for every B. Okay, so this is the definition of onto, and we also have another definition to go over, which is a one-to-one function. Okay, so we say that a function t from Rn, we'll just put it this way, Rn to Rm is one-to-one, and you can abbreviate this with a 1-1, just make sure it's clear that those are ones. If for every B in the codomain Rm, there is at most 1 x. This will be from the domain, so Rn, such that T of x equals B. Okay, so it's a related idea, right? But it is saying something pretty different, right? So other ways we can think about this. Wait, okay, let me actually write neatly. Other ways to think about this are. So this means that every B in the codomain, okay, aka target space, does not get hit by more than one vector x. Okay, so this that more than one vector x in the domain. So that means that one is okay. So having one vector corresponding to that B in the domain is okay. Not getting hit at all, so having none is okay, but twice or more is not okay, right? So it's one or none, or none, but not 2 and not more than that. Okay. So another way of thinking about this is that you have no overlapping on the target side, right? So this means that each point in the domain, or sorry, not point, we're really talking about vectors. So each vector in the domain gets its own, so I'm going to put this in quotes, but gets its own image point or image vector. Right, so no overlapping. And we can visualize this. So another way of thinking about it is to visualize it by looking at the domain on one side and the range, or really codomain, on the other side. Right. And I'm not going to draw these as vectors. I'm really just going to put little points to represent them. So you have some vectors x, y, and z on your domain side, and they get mapped. So just, these are 2 separate spaces. They get mapped over to some points on, or vectors on the range side. So wherever they get sent, right? But each of them is different. They're all distinct, right? So this would be representing a one-to-one function. And then if you want to compare that to a function that is not one-to-one, so again, starting with some points, vectors here, and you have your codomain on the other side. If you have something where, say, like x and y get mapped to the same image point, so that would mean that t of x is equal to t of y, this is not one-to-one, right? So this is not one-to-one, and that's what I'm talking about when I say there's no overlapping. So here we have some overlap, or like collapsing, right? That means that you're not one-to-one.
Is this related to the one-to-one definition we've used in regular functions? And
Yeah, it is. Yeah. The thing is that since we're dealing with linear transformations, we will have more characterizations of one-to-one functions that you wouldn't have with normal functions. So with normal functions, you really have to use this idea. We'll have some really nice ways of checking whether a linear transformation is one-to-one. That's a lot easier. Great. Okay, so I wanted to start the quiz at 1:30, but so I'm going to go for probably about 8 more minutes, 9 more minutes or something, and then open up the quiz. So, okay. Other ways we can think about this. So in terms of linear transformations, thinking about that equation, t of x equals b. So this means that for every b in the codomain Rm, t of x equals b has at most one solution. So that means that you either have a unique solution or the equation is inconsistent, right? You don't have a solution, either unique or no solution. Otherwise, you would get infinitely many solutions, right? And we can't have that. Okay. And then This is a nice way of thinking about this as well. So where A is that associated matrix, so you just form it by taking these as the columns, right? This has a pivot in every, what do you think should go here?
Column.
Column, yes. Well, we know that onto was every row and we don't really have more options than that. So yes, it is every column, but let's see why that should be the case, right? So if not, then you necessarily have a free variable. Right, so if you look at, so just a matrix like this, say this is your associated matrix, and it doesn't have a pivot in every column. You have one column where it does not, and that is associated with a free variable, right? So then if you have a free variable, you know you get this parametric solution and infinitely many solutions, no matter what B is, right? So, well, not no matter what B is, it's actually, if this matrix equation that you could form is consistent, so if this guy is consistent, it will not have a unique solution. Because of that free variable, right? But it could be the case that none of these equations, so for every B that we choose, they're inconsistent, right? That could be the case. But we do know, okay, so let me write that down. They could all be inconsistent. Okay, inconsistent. We could have that this is inconsistent for all B. Then this doesn't invalidate anything, right? So if it's always inconsistent, then we never run into this problem of having a free variable. But we do know always AX equals 0 is consistent because we always have the trivial solution, right? So this is because 0 is a solution. Okay, so we know that at least once we will run into this problem because we'll have a consistent system. That means that, well, this kind of brings us to, so this idea brings us to what I think is a very surprising result. So we have a theorem that characterizes one-to-one functions. Okay, and this says that a function from Rn to Rm that is linear, so maybe that should be in here. That is a very important part of this. So a linear transformation T from Rn to Rm is one-to-one if and only if this equation T of x equals 0, so this homogeneous equation has only the trivial solution. So this is really surprising because just from the definition, we would need to check that T of X equals B has at most one solution or none for every B, right? We would need to check it for everything. But this says that we only need to check it for one value of B or one vector B, right? And it's just the 0 vector. So, I mean, it's a very powerful result, right? So we have to do a lot less work to check if a function is one-to-one, right? So we can go ahead and prove this. Do I have enough time? I'm going to try. Okay. So first, if T is one-to-one, so assuming that T is one-to-one, then we know that T of X equals 0 has at most one solution. That's just from the definition of one-to-one. This is from the definition, right? But we know that this particular equation, because it's homogeneous, this always has the trivial solution. Right? So this has only the trivial solution because it has at most one, and we know what it is, so it must be the only or unique solution. Only the trivial solution. Okay, so that goes, sorry.
So like one-to-one means there's like at most one solution, and if it equals the 0 vector, then that only solution has to be the trivial solution.
Yeah, exactly. Yeah, so that's one way. So we showed that if it is one-to-one, then that equation has only the trivial solution. And we need to go in the other direction. So show if the, so if T of X equals 0 has only the trivial solution, we want to show that the function is one-to-one, right? Okay, so what we're going to do is suppose that we have T of X1 equals B and T of X2 equals that same vector B. So this would mean if X1 and X2 are different vectors, that means that this does not satisfy the definition of being one-to-one, right? So what we want to do is show that, in fact, so we want to show, so I might abbreviate this WTS in the future. So we want to show that we had to have X1 equals X2 if the equation T of X equals the 0 vector has only the trivial solution, right? So we want to show that, and we're going to use the fact that, first of all, T of X1 minus T of X2, each of these are equal to B. They both map to B. So these will cancel, we just get 0. Right? Next, we use the fact that T is a linear transformation. So we can combine this into T applied to X1 minus X2. Right? So now we have this equation right? Just by using the information that we have. And we know that this has only the trivial solution because we assumed that that was the case. So that means that x1 minus x2 is equal to the 0 vector, which means that x1 is equal to x2. Right? Okay, so we showed what we wanted to show, which was that t is 1-to-1. Okay, so
Oh, sorry.
yeah, go ahead.
I don't really understand how you got from t of x1 minus x2 equals 0 vector, and then this has only the trivial solution.
Okay, so when I say this has only the trivial solution, that's coming from this assumption up here.
Oh, okay.
Right, so I'm using that down here.
Thank you.
Yeah. Okay, so yeah, we should definitely start on the quiz. I have to get it up on Canvas, so give me a second to do that.